Seminar. We are recording the seminar also. Today's speaker is Fraser Goldsworth, and here is he's actually from Oxford University, and he's doing a PhD there with David Marshall, who is one of the Mercator Fellows of our project Transregio 181. And Fraser is doing his PhD thesis about symmetric instability in western boundary currents crossing the equator. Yeah, we are very eager to learn about this.
Yeah, okay, thank you for that introduction. I'm also working with, as well as David, Helen Johnson as well, based in Earth Sciences in Oxford. I'm going to talk about symmetric instability, which is a type of sub-mesoscale instability in cross-equatorial western boundary currents. And in particular, we're going to focus on the western boundary currents of the tropical Atlantic. And there's two western boundary currents in particular we'll be focusing on. But before we zoom out and start thinking about the sub-mesoscale, I think it's always really useful to kind of motivate the work by zooming out a little bit and thinking about the global scale circulations. So in the Atlantic, we have this huge global scale circulation of real climatic importance, the Atlantic Meridional Overturning circulation. This current, we have a northward flowing surface current or surface limb, which brings warm water and other climatically important traces. So it brings heat and carbon across the equator into the northern hemisphere. Then at the high latitudes, this current, we get deep water formation as a result of buoyancy forcing, and then we get this return flow in the form of a deep western boundary current. And this also has a cross-equatorial component. So the AMOC crosses the equator in both its surface and its deep limbs. So understanding how it does that is really important for understanding interhemispheric water exchange in the Atlantic. And so I guess this previous slide was, this is kind of a bit of maybe now an outdated view of the AMOC. So it kind of shows it as one huge coherent current. But actually, we know now, as a result of observations and I guess other advances in things like modeling, that it's not just one current. It's made up of lots of different we've got western boundary currents and interior circulations, and all sorts of other processes are important. And in particular, I guess in recent years, we've started to understand a bit more the role of mesoscale eddies and mesoscale processes on variability in this current. And I guess my PhD thesis, the question I've been hoping to answer with it is whether sub-mesoscale instabilities, so even smaller scale instabilities at the equator, play a role in this current system. So this is I think was almost finished with the introductory slides. So this figure here shows there's a lot going on, but it's kind of a summary of the water mass formation and transformation processes occurring in the Atlantic. And we can see close to the equator, there's a lot of dipycnal mixing, and symmetric instability, I guess, is a process which we think might be producing some dipycnal mixing and might be important, or could be potentially important in helping close this water mass formation and transformation budget. And this quote this figure's from a review paper. This quote's from the same paper, and it basically says, an important and as of yet poorly understood component of this pole-to-pole overturning cell is a transformation of potential vorticity that must take place in the northward flowing limb to convert negative potential vorticity coming from the southern hemisphere into the positive potential vorticity found in the northern hemisphere. And so what this is basically saying is that in the southern hemisphere, we have mainly negative potential vorticity, and in the northern hemisphere, mainly positive potential vorticity. And we've got a current crossing the equator, or we've got many currents, I guess, crossing the equator, and we need to find potential vorticity is it's materially conserved, and we need to account for how this potential vorticity changes sign. And again, symmetric instability is a candidate for a process which might be able to do this. So symmetric instability is really linked to potential vorticity, and we'll learn a bit more about that in a moment. And okay, this is, as I say, one last kind of slide of background. So this is the this shows the tropical Atlantic, and I guess a bit of a close-up of the current systems we have there. So in the surface, you can see we've got the northward flowing North Brazil current. So this has typical speeds of around 80 centimeters per second. And then we also get the formation of these eddies, the North Brazil current rings, which are these huge mesoscale eddies. Yeah, so and the vast majority of AMOC transport occurs in this boundary current. So around 80% of the AMOC's cross-equatorial surface transport occurs in this narrow boundary current. And similarly below it, we've got this deep western boundary current, and we can see this also breaks up to eddies after it's crossed the equator, and around 2/3 of the AMOC's transport occurs in this deep western boundary current. So these boundary currents, I guess, are really, the point here is boundary currents are really important for the AMOC. And to understand AMOC, we have to understand these boundary currents. So why symmetric instability? So I guess I've hinted that symmetric instability is a candidate for something which might produce some dipycnal mixing, which we're interested in, and it might be able to reset the potential, it might be able to change the sign of potential vorticity as these currents cross the equator. But we can do a bit of a thought experiment to understand why you might expect to see it close to the equator. So we start off with the material conservation of PV. So that means, first of all, potential vorticity is given by this equation here. So we can see we've got a planetary, a component of planetary vorticity. We have this curl of U, so this relative vorticity component. And we finally take the dot product with the gradient of the buoyancy field. So this is, I guess, our stratification in baroclinic terms. And this quantity is materially conserved. So if we measure the PV of a fluid parcel at one time, and we follow that fluid parcel around, as long as we're not forcing either the momentum or the buoyancy, we expect this quantity to remain the same. And symmetric instability is really closely linked to potential vorticity. So symmetric instability occurs if planetary vorticity and potential vorticity have opposite signs. So if we imagine starting off from the southern hemisphere, here planetary vorticity is negative. So to be stable to symmetric instability, our potential vorticity must also be negative. We can then imagine advecting this fluid parcel, which is started off in the southern hemisphere, across the equator in the form or in a western boundary current. And we'll end up in the northern hemisphere, and our potential vorticity will remain negative because it's materially conserved. But our planetary vorticity is now positive. And so this inequality, FQ less than 0, this is now satisfied. And so we might expect to see symmetric instability. And we conclude that, I guess, a PV configuration that is stable in the southern hemisphere is not going to be stable in the northern hemisphere. So yeah, I guess in short, we might expect to see symmetric instability here. And the reason we're focusing on western boundary currents in particular is that the growth rate of symmetric instability is approximately given by the square root of this equation here. So it's the planetary vorticity multiplied by the absolute vorticity. Close to the equator, planetary vorticity is very small. But so that means that for this growth rate to be large, we need this dV by dx, this horizontal shear term to be large. And western boundary currents are one such place where we expect that the growth rate will be large enough that we see the instability. And so symmetric instability, I've said it occurs in these cross-equatorial flows because of the change in sign of planetary vorticity and conservation of potential vorticity. So it's those two kind of key, those are the two key ingredients we need to see symmetric instability in these cross-equatorial flows. What this means is that symmetric instability can occur away from the surface and the bottom boundary layers. And this is different to the symmetric instability we typically see in the ocean. So typically, we require some sort of potential vorticity forcing in order to change it. So typically, we have to change the sign of potential vorticity for symmetric instability to occur. And this typically happens in either the surface boundary layer or the bottom boundary layer. And the fact that in these cross-equatorial symmetric instabilities, that we see them away from the surface and bottom boundary layers, it changes their character slightly and the way they behave. Okay, so I've spoken a lot so far about symmetric instability without really saying what it is and what it does. So symmetric instability, as we've just explained, it occurs when planetary vorticity and potential vorticity have opposite signs. And what it does is we get the generation of overturning cells. So these plots here show, first of all, on the top, potential vorticity in an idealized model of a blob of negative PV evolving over time. And we've also got the overturning stream function from that model evolving over time. And so we can see we start off after in this model with a blob of negative PV in the northern hemisphere, which we expect to be symmetrically unstable. And we see after 2 weeks, a lot of that negative PV is gone. There's still a little bit. And then after 3 weeks, we're just left with lots of PV of about 0.
Is it hydrostatic one?
This is hydrostatic. So it's barely, I think it's 2 kilometer resolution. So it's, it's not resolving secondary instabilities, but it still captures the fact that symmetric instability is setting PV to 0. And we also see that we generate these overturning cells. So this is the overturning stream function. And you can see we've got these stacked cells which are counter-propagating. And what these cells do is they mix laterally and vertically the negative PV with the positive PV. And that's what means that we end up with with PV of 0 after 3 weeks.
For turning in the solar plane.
Yes, yeah. So perpendicular. So the current in this setup is coming out of the screen. And we get overturning cells sort of within the screen, within that plane. Okay. But so these models are really simplified. We basically set all the terms in d by. We basically assume there's no meridional dependence or no meridional variation of the current. But that's not really true. So to understand exactly what's going on, we need to look to fully 3D models. So this plot here shows potential vorticity in an idealized 3-dimensional model of a western boundary current crossing the equator. What going to 3D means is that we get meridional variation. So it means we can have eddies and things form. It also means we get the beta plane, we've situated the model on the beta plane. So that means we capture that meridional variation in F. So we don't have to just put a blob of negative in the northern hemisphere. We can actually see how the negative PV evolves over time. It just kind of adds, I guess, it adds some missing ingredients. We make a lot of simplifications in this model. So I'd say it's inspired by the North Brazil current. So we approximate Brazil as a straight line. We don't have any topography, and we have open boundaries at the northern and southern edges of the domain. This image should now come to life, and we can see how the PV field evolves over time.
To the east.
Yes.
East on propagating possibly.
I think they're internal waves of some sort, because this is plotted on a 50-meter surface. As soon as you interpolate to an isopycnal grid, they kind of become much less intense. It seems that the video isn't on the next slide, so we can talk about this here instead. So we can see as the current crosses the equator, we get spinning up these big anticyclonic eddies, and these kind of pool our waters with negative PV. And then around 400 kilometers north, we start to see the excitement of symmetric instability. So we start to see these small scale pattern. Okay, so here we go. We've got a big flurry of symmetric instability right now. This is quite exciting because we're seeing the excitement of symmetric instability, and also we're seeing the aftermath of it. So we're seeing afterwards, these huge eddies have their PV set to 0. And this is also quite exciting because in real life, in the real ocean, we see huge anticyclonic eddies being spun up at the equator. And we also, in the 2000s, there was a campaign to measure their vorticity, and they found that their vorticity was 0, which I guess suggests that symmetric instability has been at play in those eddies in the real ocean as well. And so, yeah, this I guess is showing that symmetric instability is being excited in these models, which is I guess something new. And then, okay, so that's the surface current.
Resolution.
Sorry?
Resolution is the issue.
In those models. So these models have a resolution of 2 kilometers in the horizontal, and I think about it's variable in the vertical. But yes, to resolve the instability properly. Also, first of all, I guess global sort of circulation models, which we couple with climate models and things, those aren't resolving these processes yet. Some of the high resolution global models, which we kind of, I guess, some of the toy model type things. So there's some MIT GCM runs at, I think, 4 kilometer resolution. Those, in theory, would have sufficient horizontal resolution to resolve this, but they don't have the vertical resolution. So
that model is there, the resolution depends because the length scale of the fastest growing mode is the smallest, right, for symmetric instability.
Well, I guess the length scale of the fastest growing mode depends on the viscosity. And so in these models, we have an artificially large eddy viscosity. And that kind of means that you're able to resolve, it reasonably well. So I think in the vertical, the length scale is around 25 meters.
Model viscosity.
Yeah, with our model viscosity. So
what happens if you increase resolution further? Changing this picture?
It will reduce the vertical size of your overturning cells, but in the horizontal, in terms of the horizontal, the least stable mode is set by the width of the boundary current, and that pops out the linear stability analysis. So yeah, so I think lateral shear that's dominating the negative PD. That's what's causing the PV to be negative here. It's less the vertical shear. So it's, I guess, towards the inertial end of the symmetric instability spectrum.
About the homogenization, it's done by the symmetric instability.
Yes.
Differently resolved in different models.
So I guess we're clearly getting sort of, go back a few slides. We're probably not resolving the homogenization of PV correctly, no, because also we know that it's the secondary instabilities as well, which are the shear instabilities, which are sort of properly doing the homogenization. So here it is the viscosity, which is doing the mixing for us because we're not resolving that. But I guess, yeah, we're still seeing the excitement of symmetric instability in the first place.
Which is this with different resolutions, so 1 kilometer or 5 kilometer?
So 1 kilometer, we still see similar things. I've done some, yeah, so these are 2 kilometer runs. I've been looking at deep western boundary current with 1 kilometer runs. And I think it was up to about, from the top of my head, I think 8 kilometers was kind of what you needed to see anything. Well, actually, no, maybe it was 16 kilometers. Then any higher than that, or any lower resolution than that, you didn't, yeah, it was really bad.
But for higher resolution, it doesn't change.
It changes, it does change, but it's mainly the vertical extent. It's the vertical mixing which is changing. So it's the vertical size of those overturning cells.
Okay.
So, right, we're here. Okay, so since so I guess this work was this work was from a while ago using the 2 kilometer runs, and since then in the UK we've had a new supercomputer come online, and so we've been able to really up resolution a lot. And so since then I've been looking at the deep western boundary current and using these are 1 kilometer resolution models, and looking at symmetric instability in those. These plots show potential vorticity. The big one shows it on an isopycnal surface, constant with the I guess the maxima of the deep western boundary current. And you can see, I guess you can see there's this tongue of positive PV going into the southern hemisphere, and we can see there's the excitement of the symmetric instability here, and then afterwards we get the excitement of the barotropic instability and spinning up of these eddies. And these plots, I guess, show that these show vertical slices at 200 kilometers south and 500 kilometers south. And we can see here here we can see the excitement of the instability, and here we can see the PV of about 0, so the aftermath of the instability. And yeah, this is, I guess, some interesting things happen in this model. Just going to play. Okay. Maybe this isn't going to play. So this should. Okay, let's try that. Oh, the play button. Okay, it doesn't matter if it doesn't play. If you want to see the video, come see me afterwards. So this should show us a really nice video, and in it we should be able to see the excitement of the symmetric instability first, and then the eddies being spun up afterwards. And it should look quite nice, but I guess it's not wanting to play for us. And so yeah, so I guess this is slightly different to the surface current. So in the surface current, we saw the barotropic instability first, followed by the symmetric instability, and I guess we can actually, using arguments about the growth rates and the effective timescales, we can actually kind of predict this. And also we can use arguments about, in the surface current, the fact that we get the spinning up of these barotropic eddies first, that acts to suppress the growth rate of the instability as well. So it's amazing how well the scaling arguments do at kind of predicting where we see the instability and the order of the instability, which is quite nice. So, okay, yeah, so I guess so far I've shown some evidence of symmetric instability, and I've shown that it produces some overturning, but I've not really shown, and I've shown that it produces PV of 0, but I've not really shown anything else that the instability does. So this plot here shows the stratification at about 200 kilometers south in our model of this deep western boundary current crossing the equator. And we can see that, so in this model, we started off with a uniform stratification below about 1.5 kilometers. So stratification is the same everywhere. And we don't see that 200 kilometers south of the equator. In fact, what we see is we've got these large, well-mixed regions separating these these thin, high stratification mixing barriers. And we suspect that these barriers are being formed by the excitement of symmetric instability. Yeah, and this could be important in terms of, well, first of all, I guess we're changing the stratification of the deep ocean, which is generally quite a quiet place with not much going on. And also, yeah, we can see we've got these well-mixed regions, so they could also be important in terms of dissipation rates of things like turbulent kinetic energy, and I guess important in the dissipation of energy generally in the ocean. So they warranted some more investigation, in my view. And so this plot here shows the in grey, we've got the meridional overturning stream function. and in black, the density as a function of, both of these are as a function, plotted as a function of depth at this, along this pink line here. And we can see, I guess, first of all, in the density structure, we can kind of see these staircase-like features. So we can see we have these well-mixed regions where we've got similar, so these kind of vertical bits correspond to well-mixed regions, and then we've also got these slightly horizontal bits. So these are our stratification staircase, or these are our mixing barriers, sorry. And we can see in the overturning stream function, we can see we've got these stacked overturning cells, and we can see that these well-mixed regions correspond to the overturning maxima, so the centers of these overturning cells. And the mixing barriers correspond to these zeros in the overturning, so these cell interfaces. So that leads us to suspect that these overturning cells are really driving the mixing, the production of these mixing barriers and these well-mixed regions.
The overturning, that's not the overturning stream function. You said that's the meridional overturning.
Sorry, this is the zonal overturning. So this is, okay, so it's not actually the zonal overturning, it's actually the meridional component of vorticity. But it's kind of, that's pretty much the best you can do for an overturning stream function, or for a zonal overturning stream function for this 3D flow. Yeah, but it kind of tells you the same thing, I guess. Yeah. But yeah, this is I think quite exciting, so lots of people. I have lots of questions from people asking whether this was double diffusion or salt fingering, and it's not. Our model doesn't have any salt. We just have a single density tracer. So as far as I'm concerned, I'm pretty sure it's the overturning cells producing these mixing barriers.
The other way around, the mixing is producing the overturning.
Well, okay, I'll try and convince you otherwise with this slide. So this slide, I guess, is, I hope will convince you that to generate these mixing barriers, all you need is overturning cells. So we can think about a really simple model of the evolution of buoyancy over time. So we have here, this equation, we have the rate of change of buoyancy over time is given by the advection of buoyancy in the zonal and in the vertical directions. And also we have some diffusion of buoyancy as well that we need for, I guess, mixing and a bit of stability as well. So this plot on the right in color, we're showing dB by dz. And these contours show the overturning stream function, which we're prescribing for this model. So we're prescribing U and W in terms of an overturning stream function. And okay, now this should come to life, and you can see over time, all we have to do is solve this equation, and after 27 days, we can see we've got these mixing barriers already, and they've got the right sort of periodicity in the vertical. They've got the periodicity matches up with what we've seen in that previous slide from our idealized model. So this kind of, I guess, this toy model actually does, I think, I hope it convinces you that all we need to generate these mixing barriers and these stratification staircases is these overturning cells. And this, I guess, this process isn't unique to symmetric instability. Any process where we have overturning cells should, in theory, produce mixing barriers and well-mixed regions.
Let's explain again why there's change in buoyancy in the first place. It was homogeneous in the first place, right, in the initial condition. What are you using for initial condition?
Yeah, so so this isn't this is the that's the laser. Okay, so this is dB by dz. So we start off with a uniform background stratification. So n squared or dB by dz is constant. So there's a background gradient.
Right, that's advection.
Yeah.
Change.
Yeah, yeah. And so I guess what this model doesn't capture is that, so we just prescribe U and W and we keep it constant. Oops. But this doesn't capture, I guess, the dependence of UNW on the stratification, which there'll definitely be some nonlinear feedbacks there. But I think the fact that we can, this seems to capture the essence of the problem as far as I can tell.
You can only change your buoyancy if there's velocity, right? You have the velocity at the jets there, right?
Yeah, we're prescribing the velocity.
So then there's no other chance for the buoyancy to develop anomalies at the places where there's a lot of velocity. It's kind of obvious that it has to happen like this.
Yeah. But yeah, I guess my hope here was just that it kind of shows that the two key ingredients you need: overturning cells and a background density gradient. And that's kind of all we need.
Also generated differently, right, by mixing in these cells and mixing boundaries.
Yes, but that's not what we're seeing in here. That's not what we're seeing in here, though.
Now you see homogeneous buoyancy within the cells.
Yeah.
And then jumps at the boundaries.
Yeah.
Where there's no mixing.
Yeah.
So I could also say that's the mixing effect of mixing inside the cells.
Okay. Yeah. But I guess we've also got, we're pretty sure that this overturning is coming first because this overturning is being generated by the symmetric instability. So if we've got this background stratification, which is...
But there's probably also mixing generated by symmetric instability. You didn't show.
Yes, yeah, there is. That's true. Yeah. So yeah, I guess, okay. Yeah. So maybe I need to do some more work on convincing you that it's this way around. But yeah. Okay. So am I? How much longer have I got? Am I good for time? Okay. Yeah. So we can. Okay. So one of the questions I'd also been hoping to answer was about how much water mass formation and transformation the instability induces. So I guess, yeah, we've seen that we're getting a lot of mixing clearly, or we're getting some sort of mixing in these models. Yeah, one of the questions I guess I posed at the start was whether the instability has a role in the overturning budget of the AMOC. And we can think about the water mass formation framework proposed by Bennett. And in this framework, we think about the volume of isopycnals and how that changes over time. And we can the next plots I'm going to show you have a look at how the volume of some different density classes change over time in our idealized models. So this is a slightly complicated plot, so bear with me. So on the first of all, on the bottom row, so these are from just south of the equator to 250 kilometers north of the equator in our surface model of the North Brazil current. These plots are from 250 kilometers to 750 kilometers north. And finally, these plots at the top are from 750 kilometers to 1500 kilometers north. And so we expect that most of the excitement of symmetric instability in this surface current to be occurring in this kind of region. Then each column corresponds to different density classes. So here we have a surface density class, an intermediate water density class, and finally a deep water density class. And we have two model runs. We have a standard model shown by the solid line, and the dotted line shows this viscous control run, in which we've used the viscosity to suppress symmetric instability. Okay, and then what these lines show is the amount of water mass formation, or the total water mass formation that has occurred as a function of time. And so first off, I guess we see in the light water and the intermediate water classes, just south of the equator, in both the control run, so the dotted line and the solid line, we see there's not much water mass formation at all. And that's hardly surprising because I guess these are, there's nothing going on here really. We're not seeing any symmetric instability yet. Slightly further north, in this 250 kilometers to 750 kilometers region, so this is where we're seeing the excitement symmetric instability. We get a sort of a decreasing trend in the amount of surface water, and we see that we kind of have a bit of a corresponding increase in the amount of intermediate water, followed by a decrease. And then in the deep water, we see again, we've kind of got this up-downy pattern. And so I guess to start off with, what this shows is that we're losing water in we're mixing the lightest water with the intermediate waters. And then after a bit of time, the growth rate is slightly lower in the deep waters. So after a bit longer, we start to mix the waters, these intermediate waters with these deeper waters.
So this is the case with the surface boundary current.
Yeah, this is the surface boundary current.
Expect the surface densities to be mixed. But why is the effect on it deeper density?
I'd say deep. So this is below the. This is. Okay. This is. Here we go. So this is below about 250 meters. So we've still got, in our model, the current's still quite substantial there. Okay, sorry. So actually, I'll skip back to this one. So these are our three density classes. So we've got surface. Okay. That's why I was pressing the wrong button. Okay, so you've got this this surface density class, which goes down to about 50 meters, and this deep, the intermediate density class goes from about 50 to 250 meters.
All within the Western model.
Yeah. So I mean, you can see here the this 250 meter density class is still this is the velocity. It's still a substantial velocity there. Although basically, because the velocity gets weaker as we go to depth, eventually we kind of stop having the negative PV, and the planetary vorticity kind of overwhelms the relative vorticity. Yes. Okay. And so.
Fraser, sorry to interrupt, but can you try to point here so that the online audience might see this?
Oh, okay.
I don't know if it, can you try? No, it's
Yeah.
not working. Then
Okay.
you can go on like.
Does the mouse, can they see the mouse?
Yeah, they can see the mouse, but not the pointer.
No, how do I do that? Okay, previous. Okay. Okay, this is good. Yeah, so where were we? We were talking about, so we get a bit of transformation between these two, the intermediate and the deep water. I say deep water, that sub 250 meter water density class, but not a huge amount. And then finally, I guess in this furthest north density, this furthest north latitude band, in the surface we see not much at all. If we ignore the dotted line for now, in the intermediate water, we kind of have a bit of transformation between that and the deeper current. And that, I guess, is because of the growth rate is slightly smaller for the deeper current, so it has to get further north for us to actually see the excitement of the instability in the first place. But these rates are like really quite low compared to what we might expect. And I think the problem here that we've had is this is 100% to do with model resolution. So we're modeling, we're using a 2 kilometer resolution, which just isn't enough to get those secondary instabilities, the Kelvin-Helmholtz instabilities and things, which we know are really important for getting the water mass formation and transformation rates right. And so I guess in short, I mean, these are the rates that we're seeing in the model, but I think this does show the limitations of the model. in terms of, I think we've shown that the excitement of symmetric instability is almost certainly there, but I think we need better models to be able to get it right. And even, I guess, symmetric instability of this type is something which I think would be useful to parameterize, perhaps. But I guess first of all, to even parameterize it, we need to sort of work on these models a lot. And also, I guess, to even decide whether it's worth parameterizing, we need to work on these models to work out what these water mass formation and transformation rates are. So I guess this is, this kind of is, it shows that there's still work to be done here, I guess. And then I guess I've not mentioned I said ignore the viscous line in these highest latitude bands. So basically, you can see there's a lot of water mass formation and transformation happening in these high latitude bands in the viscous model. And I think that's basically, it's a combination of the viscosity is really strong, so it's going to always cause, or it's going to cause a lot more mass formation. And also, the viscosity suppresses the symmetric instability, but it can only do that for so long. And around about 8 kilometers north of the equator, it stops being able to suppress it completely. And then I guess you get a lot of pent-up energy is released, and we get the strong water mass formation and transformation rates.
Change the diffusivity, only the viscosity.
Yeah, just the viscosity. So, and also just the vertical viscosity. That basically, so you have, I guess, a competition between stratification, which wants your overturning cells to be, if you've got strong stratification, you want small overturning cells. If you've got a strong viscosity, you want big overturning cells. And essentially by upping the viscosity enough, you kind of end up just with no overturning cells. But that breaks down when you get to higher latitudes because the growth rate gets much, I guess the imbalance gets stronger. So that's I guess, I guess I'll probably leave us with, or I'll do some conclusions, but I'll leave us with that, which is kind of showing that there is still work to be done. So I guess in summary, we've seen that we might expect to observe symmetric instability in cross-equatorial western boundary currents. We've seen that in the surface North Brazil current and the deep western boundary current, which sits below it. We've also observed the symmetric instability in these idealized models. So these models are very idealized. We've made a lot of assumptions, but I guess they have the two key ingredients which we need, or the few three key ingredients which we need to see symmetric instability, which is the change in sign of planetary vorticity of the equator and the conservation of potential vorticity. That's what we need to be able to excite symmetric instability, and we've seen that. And then we've seen the effects of the instability on the potential vorticity transformation. So we've seen how even though our models aren't getting the water mass formation and transformation rates right, they are still producing PV of 0. And we've also seen that these models are generating, we're getting the generation of these mixing barriers, which might be important in terms of the dissipation of kinetic energy in the ocean. So in terms of the next steps, I think quantifying the mixing of the diapicnal velocities is going to be really important. And this will help us to answer questions such as, can symmetric instability help to close the overturning budget? And also, but also I think it's going to be really difficult because we've seen in those videos showing symmetric instability occurring, the regions which are unstable are sort of several hundred kilometers wide and several degrees from north to south, and being able to model these regions at the resolution we need is going to be a real challenge, I think. I think also looking at the dissipation rates of kinetic energy is going to be really interesting to see, particularly in the deep ocean. So we've got these mixing barriers forming there, and I guess it's going to be interesting to see whether these might act as a potential energy sink, and these are, I guess, occurring away from boundaries as well. it's in a western boundary current, but it's still hundreds of kilometers separated from the actual bottom. So that's quite interesting. I've also been looking at, more recently, at modeling wind force symmetric instability in the omega current, which is another important component of the AMOC. And I'm hoping to use some of the lessons learned from modeling these cross-equatorial currents to try and, I guess, better understand how symmetric instability in this current can help with deep water formation at the high latitudes. And finally, I guess we've seen these density staircases and these mixing barriers, but it'd be really nice if we could see those in real life. And I suspect we've already got the observations there, that we've got the data sets which probably contain these observations. But I think, CTD casts are probably the ideal candidates for their ideal data sets, which might contain evidence of this staircase formation. So I guess I'm also interested in looking for evidence of these instabilities in the real world still. Nice. So that's me done. So thank you for listening.